What's the H minimum it takes for the car to make it around the
Yeah.
Height.
Minimum height such that.
Oh, such that the car. Okay.
Negative F.
Oh. I think all that first part I actually forgot, never recorded. I recorded the break.
Oh.
That's important.
I mean, think of it
Well,
this way.
at least we
your-
got something.
I was gonna say, yeah, just record the Zoom meeting.
Think of it this way: your blunder was not recorded.
Yeah, good. That's true.
Did Pants get to see that?
And for those who are just tuning in, when he said my blunder, he was referring to just this awesome thing I did where I did a backflip. Like
Yeah,
a
I
car.
think we
Landed
mixed
on my
up
feet.
on what blunder means.
All right, so let's see if we can find the minimum height for which we have to roll this car, but let us assume that we're not, let's make it frictionless. Let's go ahead and establish.
Sorry, Dr. Fox, I can't see the problem writing.
Oh, it's too far away, I think.
Or it's my too light.
I think he needs glasses.
It's not really, it's a little, oh, I can't see the board at all.
You can't see that either.
Can't see
It's just pure
screen.
like bright white. Yeah.
All right, then let's go to plan B.
Or C, whatever we're up to now.
There, perfect.
Thank you. That's 10 meters radius.
Yes, radius is 10 meters.
Ten mom.
All right, so the minimum height, this is sort of a drop back. So we got a couple different principles involved here. We've got Newton's laws, we've got conservation of energy, we've got conservation of momentum. What approach should we take?
Find the potential energy.
Force diagram.
All right, if we did force diagram, got the car right there. What are the forces acting on it?
Weight.
Normal force of the track.
So if we wanted to do work energy, let's figure out, are either of these doing any work?
Weight.
Weight is keeping it to the ground.
Okay, but in terms of work, is it changing height?
Mm,
Isn't it rolling down the
Yeah.
ramp?
Yeah, or moving down the ramp. Yeah,
Weight.
so weight is gonna be doing some work. What about the normal force? Is it doing any work?
It's keeping it up.
It changes as it goes around, right?
What's the direction of movement of the cart?
It's moving to the, down and to the right, so the normal force is pushing it to the right.
Yeah.
It's always going to be perpendicular motion.
Yes.
So
I'm not saying that normal force can't do work here, but in this case right here, the normal force is always going to be perpendicular to the track. It's always going to be perpendicular to the movement of the object.
That makes sense.
So the normal force doesn't do any work. Y is perpendicular to, in essence, the displacement. So only thing doing work is weight. What do we know about weight?
mg.
Okay, what else?
Oh.
Weight sine theta is the magnitude of the direction of motion.
The magnitude of the force?
Yes.
Okay, weight times the sine of theta, except theta is constantly changing on this. So let me just interject here, because theta is constantly changing, it's not a straight ramp. Because it's constantly changing, using Newton's laws straight up to start doing F equals ma, it's gonna be incredibly difficult here without without knowing more information about the curvature of the track.
So, switch to different principle.
Yes?
Okay.
What is the Y? What's next to the Y?
Here?
Yes.
That's a perpendicular, that's like, I was attempting to draw that.
Oh.
The normal force is perpendicular to the displacement at any point in this problem.
Since there's no non-conservative force, do we use energy initials equal to energy final?
Yes. Weight is doing work, therefore, it is a conservative force, therefore, conservation of energy is probably the simplest tack to take. So, energy initial equals energy final. Now the question is, where are we picking to be final?
Oh,
If that's the initial, that's my initial there.
well, whenever it finishes the loop, where,
Over here?
yeah, sure.
At
That-
the intersection of.
You said,
It's on the loop.
Pat, was you, where's gonna be the trickiest spot?
The top of the ramp, the loop.
Top of the loop, yes. This is the point right here where you're going to run into the biggest amount of trouble. If you're going too slowly, then you're going to fall off before you get there. If you're going too fast, then, well, we've exceeded what we need to do. So we're trying to find the minimum height so we get to that minimum speed, so it just barely makes it over here. So final is going to be at the top of the loop. So I just have kinetic plus potential, kinetic final plus potential final. All right, it's gonna be brilliant. It's gonna be a chorus of angels.
Is there any of that like?
1/2 mv squared.
Not necessarily the chorus, but sure.
You gotta count us off, you just can't trust us to all start at the same time.
What's the formula for potential energy?
1/2 equals mg.
Oh, listen to the question.
Oh, which one?
Which one?
The one associated with this conservative force. MGH, all right. So MGH initial is equal to, all right, formula for kinetic energy.
1/2 mv squared.
It's not a race, it's a chance to do it in unison. This is gonna be beautiful. 3, 2, 1.
1/2 mv squared.
Oh, the enthusiasm. It's like you're singing happy birthday, Dirk. Chorus of fallen angels?
Is there any of that like translational or rotational kinetic energy?
No, we're just dealing with linear. No friction, it doesn't matter if there's wheels on it or not. There's no friction, so the wheels will turn, that thing's just gonna slide. Okay. We are gonna start at rest. The initial. All right, so what can we get rid of?
Initial velocity.
Okay,
Would it be,
Are we looking to cancel things here? The MG?
we can't cancel MG because there's no G here.
Can cancel mass, right?
Yes.
Could we cancel height depending on where we put our initial and final height?
Where do you want to put initial and final height? Where do you want to put H is equal to 0?
At the, I mean, if we put it at the top of the ramp, where the car starts, we could eliminate H and I, but maybe it would be best to put it like
Oh, sorry, if we put H is equal to 0 where?
at like where the car starts.
Here, okay. Do you want to do that?
would that complicate things?
Is that optimal?
Is
I
that?
would rather do like final height, because then we could have a positive initial height, right?
Yeah.
That
It
makes
comes down to what your own preference is. Putting h is equal to 0 here or here, and there's some mental sense of putting it here, but that doesn't eliminate a term. But if we want to eliminate a term here or here,
We'll go with top of the ramp.
where the car starts.
the top of the ramp where the cars, okay, so here.
Or no, I meant.
Oh, top of the loop.
Yeah, I would go with the loop.
My bad.
Oh, we
All
can
right,
do that.
we'll put it here.
You know what, never mind, maybe I meant.
So therefore, this is equal to 0 because we say so.
I like that.
So we have taken this and we have simplified it down into, let's find out how well this will show up at all. Let's go for that. And but these is this one isn't. Here we go. Hopefully this will be thicker. So we now have G. H initial is equal to 1/2 VF squared. Oh, you can't see it at all because,
Rip pants.
all right. Fans, can you see this?
Yes, thank you.
All right. It's supposed to be black instead of gray, but it is what it is.
There's some thick writing.
Was that?
And there's some thick lettering or writing there.
All right. So we're trying to find this. I know G, well, you know, I can just put it on a planet, I can figure out G, but I don't know H, I don't know V, there's 2 unknowns. What equation, 2 unknowns?
So we substitute, are there any things that we can substitute in?
Such as?
Probably not.
Is there a way we can get the radius in there? Does that matter?
Yes, it does.
This.
If you've ever done any type of rolled anything along the loop, the tighter the loop is, the more it's gonna whip around, so you don't need to start from as big a height.
Yeah. Don't know.
We equate speed to change in is distance over change in tire.
Oh, that'll get you an average speed. What are we concerned about is at the top of the loop. What's happening as it goes around the loop?
Slows down.
Okay? And then speeds up. So it's got some speed at the peak. It doesn't stop. If it stopped at the peak, what would happen?
It'll fall.
Assuming you even got that far. If you've ever worked on a swing set, you know that at some point, if you get past the, I guess, 45-degree mark, you get the jerk in the chain.
Oh,
It's always fun.
that's terrifying, I like that.
All right, let's flash back. We do have to do some Newton's law stuff here. Energy is the primary concern, but it's going around a loop. It's going around a circle.
Oh, wait,
Centripetal acceleration.
Acceleration, v squared over r or something like that.
Something like that.
Yeah.
All right, so at the top, we have the car right here. What are the forces acting on it?
Gravity.
Gravity acting
Weight.
down.
Weight, taken down.
And then
Normal
the normal
force acting the
force
same
acting
way.
up towards the ceiling.
No, it's acting
When they're
down.
acting
No,
down.
acting,
Well,
oh,
Dang.
The track is pushing on, there's nothing to push it up.
oh, okay.
We have these 2 forces acting down. We have the normal force plus the weight, and that's going to be equal to mv squared over r. So we do have r in it, and we have brought v into it. But there's one other thing about this, is I'm trying to find the minimum speed. There's something we can do to this to actually make it workable. Because right now, I've got, this equation has, well, between the two of them, I have 3 unknowns, 2 equations. Typically not a good way to go about it.
Couldn't we substitute in mg for w?
Yeah, but we can. That,
We still.
we'll have to do that eventually. That is an R there.
And then
The M's cancel.
m cancels. No?
How do you get rid of divide by m?
Yeah.
If you divide by m, then suddenly we have this term over here divided by m. You can only,
Multiply by R,
what was that?
multiply by R.
Can we just plug in R?
That still doesn't get us any closer. You're missing the trick here.
Plug in R?
Does it have something to do with the MV squared?
Oh, the normal force is 0.
If we were trying to find that minimum height, so we're at that minimum speed at the top, we are just so close to the normal force being 0, we are just skirting it. This is approximately 0 if we are trying to find that minimum height to get to that minimum speed. If I had not said we're trying to find the minimum, then it becomes a trickier problem, other than we could still, ultimately, we'd have to find the minimum to get any information.
So G equals V squared over R?
Yep. Or more importantly, V squared is equal to GR. So my problem over here becomes G times H sub I is equal to 1/2 GR.
What would you do?
And
V equals GR, because well, you have to square root it.
No, because from this equation right here, I have V squared is equal to GR.
so the initial height is 5 meters.
Dr. Fox, did you equate, normal force and weight to mv squared r? Because it's the centripetal acceleration times the mass.
Yes. Because it's going in a loop, it's circular motion. Now, well, we're gonna keep it simple like that. I'll throw in a reality check in just a moment. Somebody did miss something there, or we missed something there.